All right, all right. Any questions y'all have? Are y'all good? All right, let's look at what we're getting into today. Hmm? About to do some more graphs. All right. All right, so in graphs of exponential functions, we saw how creating a graphical representation of an exponential model gives us another layer of insight for predicting future events. How do logarithmic graphs give us insights into situations? Because every logarithmic function is the inverse function of an exponential function. So we could think of every output on the logarithmic graph as the input for the corresponding inverse exponential equation. In other words, logarithms give us the cause for an effect. All right. So to illustrate this, suppose we want to invest $2,500 in an account that offers an annual interest rate of 5%, compounded continuously. We already know that the balance for in the our account for any year t, right, can be found by the equation A is equal to 2,500 e to the 0.05 t, right? So, right, but what if we wanted to know the year for any balance, right? We would need to create a corresponding new function by interchanging the input and the output value. Thus, we would need to create a logarithmic model for this situation. By graphing the model, we can see the output year for any input account balance. For instance, what if we wanted to know how many years it would take for our initial investment to double, right? So here goes our graph that we could look at it. This is a graph of a logarithmic function. All right. So we started off with 2,500. We know that after 14 years, it will double to 5,000, for example. So now we're going to look at finding the domain of a logarithmic function. All right. This is on your homework. All right. Everything's been posted for today, so you guys can jump in right now if you want. So before working with graphs, we will take a look at the domain, the set of input values for which the logarithmic function is defined. Recall that the exponential function is defined as y is equal to b to the x power for any real number x and constant b that is greater than 0. And remember, b cannot equal 1, right? So our domain of y is negative infinity to positive infinity, but our range is 0 to infinity, all right? So in the last section, we learned that logarithmic functions, right, which is like y equals log base b of x, right, is the inverse of the exponential function y equals bx, right? So as an inverse function, the domain and the ranges are gonna switch, right? They're gonna swap. So the domain of y equals log base b of x is the range of y equals b to the x, which is 0 to infinity, and the range, right, of y equals log base b of x, right, is the domain, right, of y equals b to the x, which is negative infinity to positive infinity, right? So they switch, right? Transformations of the parent function y equals log base b of x behave similarly to those of other functions. Just as with other parent functions, we can apply the four types of transformations, which are stretches, shifts, compressions, and reflections, right? In graphs of exponential functions, we saw that certain transformations can change the range of y equals b to the x. Similarly, by applying transformations to the parent function in y equals log base b of x, we can change the domain, all right? So when finding the domain of a logarithmic function, therefore, it is important to remember that the domain consists of only positive real numbers, right? That is, the argument of the logarithmic function must be greater than 0. There's some interesting stuff right here. So for example, consider f of x is equal to log base 4 of 2x minus 3. This function is defined for any value of x such that the argument in the case 2x minus 3 is greater than 0. So to find the domain, we set up an inequality and solve for x. So I'm going to take what my log is going to, the 2x minus 3, and I want to solve for greater than 0, right? And you solve it the same way. Add 3, divide by 2, boom, right? So x is greater than 1.5, right? So in interval notation, the domain of f of x for log base 4 of 2x minus 3 is 1.5 to infinity, right? 1.5 to infinity, that's the domain. So real quick, let me give y'all some sauce. Right. Oh, what's happening? There we go. Sorry about that. All right, so given a logarithmic function, identify the domain, right? This is how you do it. Step 1, set up an inequality showing the argument is greater than 0. Step 2, solve for x. Step 3, write the domain in interval notation. All right, that's it. Let's go over an example real quick. So identifying the domain of a logarithmic shift, right? So our question here is, what is the domain of f of x of log base 2 of x plus 3? Very simply, right? I have f of x is equal to log base 2 of x plus 3. All you're going to do is take the x plus 3 and make it greater than 0. Then just solve for x. So I'm going to subtract 3 from here. What I do to one side, I got to do to the other. So I have x is greater than negative 3. So what is my domain? Is x, what is it? So negative 3 to infinity, right? Is that going to be a bracket or a parenthesis? Parenthesis, very good, right? So from negative 3 to infinity. And that's it, I'm done. That's the whole topic. All right? Nothing crazy. So I'm trying to find the domain, all of the x values that the function will exist at. So you just take whatever the function is going to and make it greater than 0, right? And then just solve, you know? You guys want to try one? I'll start y'all off easy. How about this? What's the domain here? Hmm? From what? What to what? Mhm. Two to what? To what? Good. All right. So you, okay, sorry. So you take the x minus 2, you set that greater than 0, And then you just add 2. So I have x is greater than 2. So my domain is what? It's from 2 to infinity. Very good. And that's it. What is the 1 doing to the graph? What do you think it's doing? It's, it's greater, always greater. Yeah. Not equal, greater. Yeah. Yeah. What does the 1 do to the graph? Go ahead. Right. It's shifting the graph up 1. Right? Does that affect the domain? Which is all x values? Right. Yeah. Just to make me feel good, even though I know you guys get it. What about this one? What's the domain? Right here. I write it bigger. Good. So what I do, I take the 5 minus 2x. I'm going to make that greater than 0 and then just solve for x. All right. So subtract 5. Subtract 5. I have negative 2x is greater than negative 5. Divide by negative 2. What you do to one side, you got to do to the other. So I have x is less than 5 over 2. All right.
So for log, it's not less than or greater than 2.
It's always greater than.
Or
Yeah, always greater than.
for log.
For log. So the domain is going to be from negative infinity to 5 over 2. And that's it.
Get that on the formula?
It is on the formula sheet. Questions? Are we good? Good. All right, let's keep it moving. Y'all want to try one, or you guys get the idea? Just asking for the domain of log. Y'all get the idea? Good. All right. Let's jump to the graphs. So now we're going to talk about graphing logarithmic functions. So now that we have a feel for the set of values for which a logarithmic function is defined, we move on to graphing logarithmic functions, right? The family of logarithmic functions includes the parent function y equals log base b of x, along with all its transformations, shifts, stretches, compressions, and reflections, right? So we begin with the parent function y equals log base b of x, right? Because every logarithmic function of this form is the inverse of the exponential function for the form y equals b raised to the x power, their graphs will be reflections of each other across the line y equals x. To illustrate this, we can observe the relationship between the input and output values of y equals 2 to the x and its equivalent x equals log base 2 of y. All right. So basically, I'm taking each number, let's say like -3, for example, and I'm plugging it in for 2x is equal to 2 to the x equals y, and log base y is equal to x, right? So when I plug in -3, right, I get 2 to the -3 power, which becomes 1 over 8. When I plug in -3 in the bottom, right, this becomes what? Log base 2 of y is equal to -3. And you're just going to raise both sides to the second power, so you get -3. All right? So questions on this? Mm-hmm. Got you. I got you. I got you. Mhm. So basically, they're just inverses of one another. So using the inputs and outputs from the table, we can build another table to observe the relationship between the points on the graph of the inverse function. F of x is equal to 2 to the x, and g of x is equal to the log base 2 of x, right? So you see for f of x equal 2 to the x, for example, I plug in -3, I get out 1/8, right? Plug in -2, I get 1/4, etc., right? But for the log base 2 of x, I plug in 1/8, I get out -3. I plug in 1/4, I get out -2, so on and so forth. Right? So they're reverse of each other. Go ahead. Hmm? Which one? The bottom one? For g of x equals log base 2 of x. So the y would be the g of x. What I'm trying to show you here is that for y equals 2 to the x, when I do log base 2 of x, it's the swapping of them. What was x is now y, what was y is now x. That's the point of this. It's a swap, it's the inverse of it. Hmm? So as we'd expect, the x and y coordinates are reversed for the inverse function, right? So here goes our figure to show you that. The blue line represents f of x is equal to 2 raised to the x power, but the orange line is log base 2 of x. Their reflection over the line y equals x, which is that turquoise line going across. Right? So notice that the graphs of f of x is equal to 2 to the x and g of x is equal to log base 2 of x are reflections above the line y equals x. In the middle, that's because it's being reflected over it. Right? It's a reflection over y equals x. That's what logs are. They're inverses of the exponential functions. Yeah, not so bad. Let's talk about the graph a little bit. Sorry about that. All right, observe the following from the graph, right? F of x is equal to 2 to the x has an y-intercept at 0, 1, right? So right here we're talking 0, 1, right? And g of x is equal to log base 2 of x has an intercept at 1, 0, right? Complete opposite. One comma zero right here, right? The domain of f of x, the blue line, right, is negative infinity to infinity, and it is the same for the range of g of x is equal to log base 2 of x. But the range of f of x is equal to 2 to the x is 0 to infinity, is the same number as the domain, which is g of x is equal to log base 2 of x. So characteristics of the graph of the parent function. So f of x is equal to log base b of x. For any real number x and constant b greater than 0, b cannot equal 1. We can see the following characteristics in the group, excuse me, in the graph of f of x is equal to log base b of x. It's a one-to-one function. Vertical asymptotes happen at x equals 1. Domain is 0, range is 0, right? Excuse me. Domain is 0 to infinity, range is negative infinity to infinity. X-intercept is 1 comma 0. And I need a key point, which is going to be b comma 1. B is whatever your base is. So the base comma 1. Y-intercept is none, increasing from if b is greater than 1, your base, decreasing if your base is less than 1, but bigger than 0. That's what decreases. Questions? Good? Sure, go ahead. I want to show you guys a graph after. Just want to show you all what this means. Really? It's not so bad. Yeah. I got you. I got you. So look at this, right? I got two graphs over here, right? The one on the left, right? That's going to be my log base b of x, right? When b is greater than 1. So what points do I need? I need the x-intercept, and I need one point that's on the graph, right? Let that point be whatever the base is, comma 1. On the opposite graph now, this is log base b of x where b is less than 1. So like a negative number, for example. This is the graph. I need 2 points on there. I need the x-intercept, and I need one other point on the graph. That's it. Questions on this? Good? Huh? Mm-hmm. Step 4 shows how changing the base b in f of x is equals to log base b of x can affect the graph. Observe that the graph compresses vertically as the value of the base increases, right? And note, recall that this function is a natural log of x and it has a base of e to the 2.718. Okay. The blue line is with base 2. The ln of x, that's going to be with base e. And the regular just log of x is going to be with base 10. Okay. So all three of these have they have different bases, right? and they're greater than 1. The red one is base 10. So that's like log base 10 of x. Good stuff, good stuff. Let's say you had to do this yourself. Give y'all a little bit of tea. So given a logarithmic function of the form f of x is equal to log base b of x, we want to graph the function. Here's how we do it. Step 1, draw and label the vertical asymptote x equals 0, right? Step 2, plot the x-intercept, right, which is 1 comma 0. Plot the key point, which is going to be whatever the base is minus 1, right? Draw a smooth curve throughout the points, and then state the domain, right, and the range, right, and the vertical values. Excuse me, and the vertical asymptote, excuse me, x equals 0. So domain and range is important, and then the vertical asymptote. That's it. Sure. This one or the one before? Okay. All right, let's look at an example. So we want to graph this logarithmic function of the form f of x is equal to log base b of x. So we want to graph f of x is equal to log base 5 of x. And we want to state the domain, the range, and the asymptote. So what do we do? Huh? Put the x's, right? So the first one I want that x-intercept. Right. So we have 1 comma 0, right? Or you could just say, what is f of 0? Which should be log base 5 of 0. All right. Wait, let me think about that. Hold on. That don't make sense. Hold on. That don't make sense. The 1, right? F of 1, which is log base 5 of 1, right? That's the same thing as saying what? 5 raised to the x power is equal to 1. And we know that 5 raised to the 0 power gives us 1. So x equals 0. That sounds weird. That should have been y. I'm sorry. Let me put y back here. Now that makes more sense. Y equals 0, right? So when x is 1, y is 0. That's a point. Right? And then another point that we have, right, is whatever the base is at 1. So our base is 5, and that's going to be at 1. All right. What is my asymptote? Hmm. So, so vertical asymptote, right? And what is it going to be? Right. X equals 1, right? So if I'm going to graph this now, I already know this is the x-axis, this is y, right? So x equals 1 is literally the y-axis. So it's like here. We'll just do it like that, right? So that's x equals 1, right? 2 points that I need. I'm trying to think how I'm gonna do this now. This is gonna be 1 right here. 2, 3, 4, 5, and then that's 1. So the points that I need 1 comma 0. That's right here. Then I need 5 comma 1. That's right here. After that, you can do your graph. Wee. That's it. Wait, hold on. Like this, I meant. There you go. You keep getting what with the horizontal? I got you. So look, horizontal is like horizon. Like if you're at the beach and you look out, horizon is like that. So Y's are horizontal. Yeah. And then X's are verticals. Yeah. Yeah. Nah, it's a flip. Yeah. Yeah. I got you. I got you. Yeah. Because you're confusing like what they measure, if that's the right word, with the axis itself. You know? Yeah. Yeah. Got you. I mean, yo, if you want the easiest hack for Math 30, right? Tell you right now, you take your calculator, right? Type in the function, look at the table of values. Every lesson here is me trying to describe to you how to not do that. But if all you do is take the calculator, type in a function, look at the table of values, that's the answer to every question. Like legit. Yeah. Yeah. Not even a regular one, like the one that she has, like you could do it too. You know? Yeah. But she got the bomb one right there. That's what I'm talking about right there. Yeah. And that's rechargeable too, right? Yeah, that's the fire. Yeah. That's all you need.
Go for the test, you got to charge your calculator.
That would suck. But it could work while it's on the charger, so you can just sit on the wall and plug it in. Like we got outlets over here. You know? Very long time. Yeah, it's a good battery. Better than my phone. Yeah. Yeah. That thing is better than my phone. Keep it 100. Right? Yeah. I thought. There we go. So that's it in a nutshell. Boop, boop, boop. Do y'all want to try? Huh? The homework for this? It's posted already if you want to take a look at it. Yeah. Huh? Yeah. Huh? All right, so let's do this together then. That's perfect. All right. What's the domain gonna be here? It's a log function. So what's the domain? Or you could tell me how to make it. How do I do the domain? Zero to infinity, right? So you take whatever is going to and you make it greater than zero. So domain is what again? Zero to infinity. Good. What's the range? Very good. RANGE. That's how you spell it, right? So negative infinity to positive infinity. Good. What's the asymptote here? Good. You could even go a step further and type in the calculator, click enter, and see all of this. It's there. All right. What is it? It is. Yeah. No. It could go with the regular calculator too. All you gotta do is look at the table of values and that's it. No, not yours. No. I had your calculator before. That was my first calculator when I was in high school. I used to love that joint, man. Yeah, man. That's love right there. I remember that one, man. I remember that one. All right. So that being said, right? About to start the graph. But I forgot my two special points. Shame on me. All right. So what's one of the points? Zero, right? So 1 point is gonna be, if I say one is equal to log 1/5 x, right? Something like that, right? Wait, am I saying that right? Let me think again. Wait, no. Let me try it like this, right? Rewrite this. This is gonna be 1/5. I'm just gonna put in parentheses because I don't want to be confused, right? Raised to the y power is equal to x, right? So if I make the y 0, and I know that x is going to be equal to 1, right? Because anything to the 0 power is 1, right? So what's one of my points, right? 1 comma 0. That's 1 point. Always give me that point, right? Always. But this is the reasoning behind it, right? Next. All right. Another point that you have, whatever the base is, our base is what? 1/5? Whatever our base is, comma 1. Whatever our base is, comma 1. Why is that? All right, let's take a look at that. Looking back at this function right here, right? So, what I'm telling you, if you have 1/5 and you raise that to the 1 power, you're going to get back what? 1/5. So that's why this is my second point right here. Yeah. Yeah. So now look, these are the 2 points that I want on the graph. Oh yeah, also the access, right? So let's do that. So it's just so y'all can see, right? So my asymptote is x equals 0, right? Then let's do them points now, right? So I need 1, and then it's gonna be kind of hard to do 1/5. Let's make this a 1 over here. All right. So 1 comma 0. Yeah, it's a fraction in between 1. So it's gonna be somewhere like over here. I don't know. It's gonna be over here, then somewhere like up here. Little funny. Yeah, that's a little funny, that one. So what's happening in this, right? Let me choose a nice color. What color am I going to choose? Let's do purple. All right. This is my graph over here. Coming down, going to cross them 2 points, and then boom. And you know what I forgot to do? Forgot to label my points. This is the point 1 comma 0. And this is the point 1/5 comma 1. All right. And there goes my graph. All right. The reason why this graph looks like this, you see how the base here is a fraction, 1/5? This is like decay, right? So this is why it's going to like negative infinity down. If it was a whole number, then it looks the other way, or going up. That's it. Notice how the point that I plotted here kind of is in between 0 and 1 is high up, so that's how I knew it was gonna look like this. You know? Use the points to guide you, right? Or use your table of values. Yeah. Mm, not quite. Like the sideway parabola technically is illegal because that's not a function, you know? But yeah, it's the inverse of 1/5 to the x power. That's what this is. Fun stuff, fun stuff. Yeah,
It's very easy to gauge for other.
yeah. Especially when you start talking about the transformations of this. Oh Lord, here we go. Right? So as we mentioned in the beginning of the section, transformation of logarithmic functions behave similarly to those of other parent functions. We can shift, stretch, compress, and reflect the parent function y equals log base b of x without loss of shape, right? All right, this the challenging part right here. Not gonna lie. But here we go. We gonna do it. We gonna do it. All right. So first thing we're gonna do, graphing a horizontal shift of f of x is equal to log base b of x, right? Without me going into it, right? I'm about to get into it in a second, but if it's a horizontal shift, what's happening? Yeah, so it's gonna be going like this. So I'm gonna be adding something to the thank you. That's it. All right. I feel like skipping this whole section right now because you get it. But all right, let's go through it, right? When a constant c is added to the inputs of the parent function f of x equal to log base b of x, the result is a horizontal shift c, units in the opposite direction of the sign of c. And it is the exact same shift, right? So if it's negative, it's going to the right. If it's positive, going to the same thing, right? To visualize horizontal shifts, we can observe the general graph of the parent function f of x equals to log base b of x, and for c greater than 0 alongside the shift left, right? And g of x is equal to log base b of x plus c, and that is a shift to the right, right? Blah, blah, blah. Let's take a look. Even though I feel like you all know this already. Just picking up where we left off, right? So if I have g of x is equal to log base b of x plus c, right? So I have my parent function, right? And I'm going to be shifting it over to the left, right? So a couple of things to talk about here if I'm shifting to the left, right? We see that the asymptote has changed. It's no longer x equals 0. It's actually x equals negative c, right? That's something to note, right? Also, my points, my special points that I needed, right? Those have changed also, right? So instead of 1 comma 0, it's now 1 minus c comma 0, right? And my other special point, right? Instead of it being b comma 1, is b minus c comma 0. The base minus whatever you're adding or subtracting, whatever, comma 1. So that's the shift to the left. Let's look at the shift to the right. In the shift to the right, you're gonna have h of x is equal to log base b of x minus c, right? So notice now the asymptote has changed again. The asymptote is no longer x equals 0. The asymptote is x equals c, right? And then also my points have changed as well. It's no longer 1 comma 0. It's now 1 plus c comma 0. And it's no longer the base, comma 1. It's now the base plus the constant that you're adding to it, comma 1, right? So the asymptote changes to x equals c. The domain changes from c to infinity, right? Now it's different from c to infinity, but the range is the same. Negative infinity to positive infinity, right? So the domain changes, the asymptote changes, and the points change when we shift to the left or the right. Mhm. Don't stress, you can verify this in the calculator. Mhm. So horizontal shifts of the parent function. So we have f of x is equal to log base b of x. For any constant c, the function f of x is equal to log base b of x plus c, right? It shifts the parent function y equals log base b of x left c units if c is greater than 0, right? Right. So whenever c is positive, we're going to the left, right? It shifts the parent function y equals log base b of x to the right of c units, right? If c is less than 0. So if I have like x minus 2, I'm going to the right 2 units, right? That's what that means. It has a vertical asymptote at x equals negative c, right? So whatever the shift is, vertical asymptote is going to be at positive negative c. It has a domain of negative c to infinity, and the range is the same, negative infinity to positive infinity. All right. That's the horizontal shift. Mhm. Hmm? I know it's a lot. Yeah. Pretty sure part of this is on your formula sheet too. No, don't worry. Can't find it? I got you. So, I mean, it's on the announcements. Every time I put an announcement, I put it up. Yeah. All right, so given a logarithmic function with the form f of x is equal to log base b of x plus c, we want to graph this translation. So we want to identify the horizontal shift. So if c is greater than 0, so that means it's positive, right? We're going to shift the graph to the left, c units. If c is less than 0, negative, right? We're going to shift the graph to the right, c units. Then you want to draw the vertical asymptote, which is going to be x is equal to negative c, whatever it is, right? And then you want to identify 3 key points from the parent function and find new coordinates for the shifted functions by subtracting c from those x coordinates, right? Then you want to label the 3 points. The domain is negative c to infinity. The range is negative infinity to positive infinity. The vertical asymptote now is x equals negative c. Good? It's all right. You'll get your practice. Don't worry. Let's take a look. So we want to sketch this function right here. F of x is equal to log base 3 of x minus 2, right? So alongside this parent function, right, we want to include the key points and asymptotes on the graph and state the domain and range. Okay. So a little complicated, right? First, they want us to graph the parent function. So let's do that real quick, right? So for the parent function, oh, by the way, the parent function is f of x is equal to, I'm going to say log base 3 of x. Should I say 3 of x? Nah, let me just say log of x. Call it at that, right? So we already know how that's going to look, right? Let me change my color real quick. It's going to come down. It's going to cross at some point and go up here, right? This point that it's crossing at, this is 1. And we know that that point is going to be 1 comma 0. And then this one is base 10. So I'm just going to say 2, 3, 4, 5, 6, 7, 8, 9, 10. This really isn't drawn to scale. Go ahead. Right. Yeah. Mm-hmm. Yeah, this one's a little tough right here. This is gonna be that point 10 comma 1. The log. Yeah. Mhm. Yeah. So whenever you don't see me write a base, that's base 10, period. Right? Always. So boom, there you go. That's the parent function, right? Let's get to our question now. So our question is f of x is equal to log base 3 of x minus 2. All right? I'm going to rewrite this as y is equal to log base 3 of x minus 2. Right? Said a little differently, this is 3 raised to the y power is equal, excuse me, to x minus 2. Right? Now, why am I doing that, right? What I want to know is, let's say that I make y 1, right? Let's say I'm plugging in 1 for y. So this is going to be 3 raised to the 1 power. Well, 3 raised to the 1 power we know is what? That's just 3, right? So if I say that that's equal to x minus 2, add 2 here, add 2 here, right? This is 5 is equal to x. So what did I just find? When x is 5, right? Y is 1. That's one of my points right there. You know? Let's try another one, right? What if I made y equal to 0? Say 3 to the 0 power, right? Is equal to x minus 2. 3 to the 0 is what? Is what? 1, right? It's 1. So this becomes 1 is equal to x minus 2. So I'm going to add 2 here, right? What I do to one side, do to the other. So this is 3. So what did I just find out? I found out that when x is 3, right? This is going to be, is it 1? No. Oh, you know, it's 0. No, I'm right. Yeah. Yeah, the y is 0. Yeah. Those are my two special points that I'm gonna make on the shifted graph here, right? Also, what's my asymptote gonna be on this graph? So my original asymptote we knew was x equals 0, right? So now I'm adding a -2 to it, right? So what is it? What is it? Not -2, +2. That's it, right? +2. This is my new asymptote right here. So remember, it's x equals whatever -c is, right? In our case, c is -2. So this is x minus -2, which becomes +2. All right. All right. I need another color. I'm going to do the turquoise color here, right? Um, I need some points. I need some points. So I have 5, 1. So that's 1, that's 2, 3, 4, 5, and then 1, which is up here. All right. And that's the point 5, 1. And then I have 3, 0. So this is 1, that's 2, this is 3 right here. This is the point. Let me put on the bottom. Put on the bottom. This is the point 3, 0. And then let me get another color. Let me get another color. Let's do the rainbow one because that looks like a winner. Right? Boom. Then we come up, go across, and then boom. That's our function right there, right? So this is f of, I'm just going to call it y, just for space. Y equals log base 3 of x minus 2. There you go. That's the rainbow one. Blue one is our parent. This is y equals log of x. Whew. Questions on this? All right. So we showed the original function and then we showed the shift. All right. It got shifted horizontally to the right 2 points, right?
So then you use bottom to Kirchhoff.
Yeah. Why did it have -2? Oh, that's a formula. I understand what you're asking. That's the formula right here. Vertical asymptote is x equals -c. Always. So our c in this case is -2. So you just plug it in. So minus of -2 is +2. Yeah. That's it.
But you see, S equals, our isotope is 2. But the graph is shifting to the right.
Yeah, the asymptote got shifted to the right 2 units. Yeah, so the orange line, that's our asymptote, right? Originally, the asymptote was x equals 0, but this now got shifted over to the left 2 spots. So, yeah. Mhm. Yeah. Probably just one. Yeah. It's kind of complicated. I don't know. This is not my favorite section, I'm not gonna lie. Yeah. The next section after this though? Yeah, that's the fire section. This one's like, we gotta do it. Huh? Yeah, for Thursday. Yeah. Test 4, then the final. Yeah. I'm trying to make it Monday. Yeah. I could do Tuesday if y'all want to do it that way. Yeah. Test 4, everything. Everything. Thursday's the whole final. Yeah. I mean, it's to help you out if you have to drop a test. It is to prepare you for the final too. Yeah. Yeah. I dropped the lowest test. Yeah. Yeah. Huh? Nah, I can't. Can't drop the final. Yeah. Y'all want to see an example? Or y'all feel like y'all good? You know another one? There you go. I understand. It's a little for mine too, for me too. All right, let's try it out. Yikes. You didn't say the damn parent function thing. All right. Let's call that one. Boom. And then I don't know. Let's just say that there's some point B here. Whatever. Because that's the parent function. That's why. Oh, yeah. This is 3 comma 1. I'm sorry? Log of whatever base to X. Yeah. But this one that we got is gonna be +4, so there's gonna be a shift there. Yeah, that's the more interesting one. That's what we really want to do. But this question kind of ruins it because they want you to do a parent function with it. Whatever. Yeah, so we got the point 1 comma 0, and I forgot to label that. And we got the point 3 comma 1. Yip de doo. All right, let's get back. Let's get to our real question. So I got f of x is equal to log base 3 of x plus 4. Right? Let me rewrite this because I don't understand how to do it. Be quite honest. This becomes 3 to the y is equal to x plus 4. And all we want to do, we want to plug in two numbers for the y. I want y0, I want y1. It's that simple. That's my 2 points. Something y0, something y1. Can't get no easier than that, right? So let me do the first one with 0, right? So if y was 0, anything to the 0 power is 1. So this becomes 1 is equal to x plus 4. I'm going to subtract 4 here. What I do to one side, I got to do to the other. So -3 is equal to x. So bam. So that's 1 point. Yeah. No, that's not the asymptote. That's the x-intercept. Yeah, x-intercept. Yeah. We're going to get to the asymptote, though. We're going to get to the asymptote. So now, um, what am I trying to say? 1, right? Let's do the other one. So I have 3 to the 1 power is equal to x plus 4. So that's going to be what? 3 equals x plus 4, -1, right? Subtract 4, get -1, right? So that's -1. Light work. Let's talk about the asymptote. Asymptote, I got x plus 4 greater than 0. What am I going to do here? Subtract 4 from both sides. So x is greater than -4. Wait, that's the domain. My fault. But still, that helps. I need it to be greater than -4. -4 is the asymptote, right? So boom. Let's figure out how we're gonna do this now. 1, 2, 3, 4. Right? I'm gonna get some orange going. That's my asymptote right there. Let me start at the top. Ba, 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 ba. Not the best artist. This is going to be x equals -4. That's my asymptote, right? What's my 2 points at? Get my turquoise color going on. So I got -3, 0 right here. This is the point -3, comma 0. Next one I got -1, comma 1. That's right here. It's the point -1, comma 1. Right there, right? And then we want to go up from the asymptote. Bring it up, bring it up, bring it up, boom. And we're just going off this way. That's it. Right? Questions on this? Mhm. Mhm. I'm just making it easy. I don't know. The B to the X was the hints, the OG. But all right, let's move on. -4 is the asymptote. Yeah. If you want to use a shortcut, go ahead. You can do that. Yeah. I'm not opposed to that. I'm not opposed to that if that helps you to understand it, you know? All right, let's talk about vertical shifts. A little bit right here. Okay, there you go. I accidentally found a domain there, but low key the domain contains the asymptote. So boom. Boom. But technically the formula for the asymptote is x equals negative c. C in this case is positive 4, so it's negative 4. That's the shortcut, you know? Which one? The what? Oh yeah, because it's easy. It's so easy. This is not that topic. This is not that topic. You would see me smiling when we get to that topic. The graph is the one above it. Yeah.
I think you want to put the graph in the example. Yeah.
Oh, yeah, the graph's gonna be everywhere.
I don't.
You will put there.
Me personally, I don't like graphs. It is what it is.
Oh, and the last one.
No,
The last one had graphs on it.
yeah.
Yeah.
For those
Yeah.
the graph.
So what, like, you gotta do the vertex, the so X intercept, Y stuff.
Mhm. The worst part about it, it was all on the formula sheet and nobody looked at it.
Nobody got it.
Nobody looked at it.
We don't have that.
3 hours is not enough?
Get that one. You don't have time to look at. They have a lot. So how?
But it was less questions in 3 hours.
If you but how many times you would do doing your final?
I mean, you have time, don't worry.
No, you don't have it. Six to the final will be a lot. Then yeah, a lot.
It might be easier than you think.
I don't. I don't
Yeah.
think.
Might be easier than you think.
No, I don't.
Well, we'll talk about it. All right, so look. When a constant d is added to the parent function, f of x is equal to log base b of x, the result is a vertical shift, d units in the direction of the sign of d, right? So to visualize vertical shifts, we can observe the general graph of the parent function, f of x is equal to log base b of x, alongside the shift up. G of x is equal to log base b of x plus d, and shift down, h of x is equal to log base b of x minus d. Right? Let's take a look at what we're talking about here. So, sometimes we need to see the picture to make sense of it, you know? So here you go. Yeah. That's easy, the exponential. So look, shifting up, right? So our parent function is right here, log base b of x, right? Where we have 1, comma 0, b, comma 1, right? If we're shifting this up, right? Our points are gonna shift also. We're gonna have b to the negative d power, comma 0, and b to the 1 minus d power, comma 0. That's how, this is a vertical shift, right?
Okay.
Yeah, this,
Because D is negative, like.
right, if d is, no, this is if d is positive, this is plus d,
No.
yeah. But if d was negative, right, so say minus d, right? Then we're gonna get shifted down, right? Our points will shift as well, right? So our initial point is just gonna be b to the d power, and then our other point will be b to the 1 plus d power, comma 1. That's it. That's turned on. Hmm?
That's why.
You'll see, you'll see. Just wanna make a couple notes before we jump further. All right, so for the positive d, right? I want you to notice something. The asymptote, huh? When it's like the logarithm plus d, right? The asymptote remained the same as x is equal to 0. The domain is still 0 to infinity, and the range is still negative infinity to positive infinity. The only thing that changed was the points that we plug on, that we plug into, that you have to show, right? What about when the d was negative? The same thing. The asymptote remained the same at x equals 0. The domain is still 0 to infinity, and the range is still negative infinity to positive infinity. No change there. All right. Real quick, I just want to sum this up for you. This part. That was a lot to take in. So for a vertical shift of the parent function, y is equal to log base b of x. For any constant d, the function f of x is equal to log base b of x plus d. It shifts the parent function up d units if d is greater than 0. It shifts the parent function down d units if d is less than 0. It has the same vertical asymptote at x equals 0. It has the same domain at 0 to infinity and the same range from negative infinity to positive infinity. All right. No change in that regard. Before we jump into this, let me just give y'all a little bit of tea. All right. So this is a little how-to. Given a logarithmic function of the form f of x is equal to log base b of x plus d, we want to graph that translation, right? So this is how you do it. First, you want to identify the vertical shift, right? So if d is greater than 0, positive, right? It's going to shift the graph f of x equal to log base b of x up d units. If d was less than 0, negative, it's going to shift the graph f of x is equal to log base b of x down d units. All right. You want to draw the vertical asymptote at x equals 0. We already know how to do that. Identify 3 key points from the parent function. Find the new coordinates for the shifted functions by adding d to the y coordinate. Label the 3 points. The domain is 0, comma infinity. The range is negative infinity to infinity. And the vertical asymptote is still x equals 0. All right. Now, after all of that, let's try it. All right, easiest way to do this one. Let's say that I had a parent function. F of x is equal to log base 3 of x, right? Say that that was our parent function. You already know which points we have, right? We have 1, comma 0, right? And then we have 3, comma 1, right? Just given that. Okay. You want to subtract 2 from the y values of this, all right? So that being said, right, for my shifted function, right, this is going to be the same 1, but instead of 0, it's going to be what? 0 minus 2, which is negative 2, right? The same 3, just minus 2, which is what? Negative 1, right? And that's it. You know, can't beat that, right? Of course, you know, they want you to graph it, blah, 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 right? But y'all get the idea, right? I'm gonna have a point at 1, comma, -2, right here. I'm gonna have another point at 3. Hold up. 2, 3, comma, -1. Right there. And then you already know what's gonna happen. Negative infinity, bop, 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 right there. And that's it. Questions on that? Just change the y value. If it's adding to it, add to it. If it's subtracting from it, subtract from it. That's it. All right. All right. Now, once again, it has the same domain, the same range, the same asymptote, blah, blah, blah.
But if you said check the graph, you need to give all this vertical asymptote and horizontal asymptote, right?
Well, just vertical asymptote, because of the log. Yeah.
They don't have horizontal asymptote.
No horizontal. This thing goes on for infinity, all right, in the range. So there's no horizontal asymptote. Yeah. If there was a horizontal asymptote, there would be a break in the range. But the range is from negative infinity to positive infinity. All right.
So they have horizontal shift, right?
This is, yeah.
Horizontal shift.
No, this is vertical shift. Oh,
To check the graph, you need vertical shift and horizontal shift.
right.
And
Depending on the question, yeah. Yeah. Some questions might have both. Like say you had like log base 3 of x minus 2, and then a minus 2 on the outside. That's both shifts, vertical and horizontal. Yeah.
You said just find the check the graph.
Then you just draw the graph and that's it.
I need to drop the back like this, or
Mhm.
need to drop.
Oh, that's it. Yeah. Yeah. You don't need to put the parent function with it. You could just draw that. I get it. But I need some points on the graph. Don't just draw it. I need points on the graph. You know? All right. Let's go on to stretches and compresses. Yay. So graphing stretches and compresses of y equals log base b of x. So when the parent function f of x is equal to log base b of x is multiplied by a constant a greater than 0, it's positive, right? The result is a vertical stretch or compression of the original graph. To visualize stretches and compressions, we set a greater than 1 and observe the general graph of the parent function f of x is equal to log base b of x alongside the vertical stretch g of x is equal to a times log base b of x, and the vertical compression, which is h of x, is equal to 1 over a log base b of x. All right. All right, let's take a look at the graphs real quick. And I mean real quick. So there you go. All right. We have our parent function, log base b of x, we're multiplying it by a positive a number, whole number by the way. So what happens? Our points shift, they become b rate, which is the base, raised to 1 over the a power, comma 1. That's going to be our point right there. But notice we retain the same right? The same x-intercept point. It's just our b term that's changing here, right? Let's say for the compression now, right? Which means that it's going to be h of x equals to 1 over a log base b of x, right? Our new b term, right, will be b raised to the a power, comma 1. And the same x-intercept term right there, right? Yeah. That one? Yeah.
Yeah.
You're welcome. Yeah. Before we move on, just want to make some comments real quick. All right. So when I'm multiplying it by a constant number, right? Notice that the asymptote remains at x equals 0. The x-intercept is still 1 comma 0. The domain is still 0 to infinity, and the range is still negative infinity to positive infinity, right? When I'm multiplying it by a fraction, like 1 over a, the asymptote is still x equals 0. The x-intercept is still 1 comma 0. The domain remains 0 comma infinity, right? And the range is still negative infinity to positive infinity, right? So this is when you're multiplying the term by a number, right? The only thing that changed was that b, b comma 1 term, right? So become b to the a comma 1. That's it. Real quick, vertical stretches and compressions of the parent function. We have y is equal to log base b of x for any constant a greater than 1. The function f of x is equal to a log base b of x stretches the parent function y equals log base b of x vertically by a factor of a if a is greater than 1, compresses the parent function y equals log base b of x vertically by a factor of a if a is between 0 and 1, has a vertical asymptote at x equals 0, same thing, has an x-intercept of 1 comma 0, same one, has a domain of 0 comma infinity, and has a range of negative infinity to positive infinity. Okay. Let me give you guys a little bit of tea. All right, so a little how-to. So given a logarithmic function with the form f of x is equal to a log base b of x, where a is greater than 0, you want to graph the translation. So step 1, identify the vertical stretch or compression, right? So if the absolute value of a is greater than 1, the graph of f of x equal to log base b of x is stretched by a factor of a units. If the absolute value of a is less than 1, the graph of f of x is equal to log base b of x is compressed by a factor of a units, right? You want to draw the vertical asymptote at x equals 0, identify 3 key points from the parent function, find new coordinates for the shifted functions by multiplying the y coordinates by a, label the 3 points. The domain is 0 to infinity, the range is negative infinity to positive infinity, and the vertical asymptote is x equals 0. That's simple. All right. It's the same rules, same thing. If you want, you could even play with the table of values and then just do this easily. Let's look at an example. Bear with me 1 second. Here we go. Okay. So I want to sketch the graph of f of x is equal to 2 log base 4 of x alongside its parent functions, right? We want some key points, asymptote on the graph, all that good stuff, right? So what could I do here? Let's say our parent function is f of x is equal to log base 4 of x. Right? So we already know we're going to have some points here. This is going to be 1, comma 0. And we're going to have another points, 2, 3, 4, 1. This is 4, comma 1, right? Our graph is going to have asymptote at x equals 0. Bam. That's our parent function, right? So now let's talk about our actual one that we have. F of x is equal to 2 log base 4 of x, right? I'm going to cheat a little bit. Anytime I have a number in the front, I could rewrite this as y is equal to, I'm going to take this and make it a power. So this is going to become log base 4 of x squared, right? Let me rewrite this right now. This is going to be 4 to the y power is equal to x squared, right? That's simple, right? So if I made y 0, I mean, you guys already know my game plan, right? Y 0, y 1. That's literally it, right? So if y was 0, so this is 4 to the 0 power is equal to x squared. Anything to the 0 power is 1, right? So this is 1 equals x squared. Square root both sides. I got x is equal to what? Plus or minus 1, right? In this case, there's no minus 1 because of the range, right? Not the range, excuse me, because of the domain, excuse me, right? So this is just 1, right? Let's try it again. Say I make 4 equal to 1, and that's equal to x squared, right? I want to get x by itself. I'm going to square root both sides. So I do the one side, do the other. What does that equal? Plus or minus 2, right? But because of the domain, I can't entertain the negative 2, so just positive 2. That's it. So let me plot these 2 points. I got 1 comma 0. That was there already. I ain't even got to redo that, right? 1 comma 0. Next one is 2. It's 2 comma 1 right here. 2 comma 1. And it's the same thing, right? We go into negative infinity, gonna come up, come up, come up, and then we going out. Boom. That's it. So this is y equals 2 log base 4x. Not too bad, right? That little trick thing, yeah, I'm gonna teach y'all that in the next section. All right. But that's it. That's the same process to answer all of these. You know, get them 2 special points, boom, boom, and we good to go. Oh Lord, do I want to do this? Yeah, let me do this. Combining the stretch and the shift. Yippee. F of x is equal to 5 log of x plus 2. All right. All right, I'm getting lazy here. All right. This is 5 log x plus 2. I'm going to rewrite this as y is equal to, all right? I'm going to move this to a power. This is going to become log of x plus 2 raised to the 5th power. Let me rewrite this as, what's my base? Somebody tell me. Very good. Proud of y'all. So that's going to be 10 to the y power is equal to x plus 2 to the 5th power. Y'all already know what I'm looking for, right? Something comma 0, something comma 1. Same thing. So if I have 10 raised to the 0 power, what is that again? Somebody help me. That's 1, right? So this becomes 1 is equal to x plus 2 raised to the 5th power. Solve for x, right? This is going to be the 5th root of this. That's going to cancel out. 5th root of 1. This is 1 is equal to x plus 2. Subtract 2. What you do to one side, you do to the other. Negative 1 is equal to x. Boom. Light work. Right? All right, let's get the other one, right? So I have 10. Let's say raised to the 1 power is equal to x plus 2 to the 5th. All right? What am I going to do? 5th root? Get rid of the 5. This is going to be the 5th root of 10. I don't know what that is. Y'all got calculators, right? So 5th root of 10 is equal to x plus 2. Subtract 2. What you do to one side, you do to the other. Y'all should verify if this even works. So 5th root of 10 minus 2. That's equal to x. Huh? These are the 2 points that you're going to show on the graph. Yeah. So this is 5th root of 10 minus 2. Let's talk about the asymptote, now that you mentioned it, right? How do I find the asymptote again? Yeah, go ahead. Easiest way, I think, to find the asymptote, find a domain, right? So x plus 2 greater than 0. Subtract 2, subtract 2. I have x is greater than negative 2. What's my asymptote? Don't overthink it. What's the asymptote? No. Negative 2. That's it. That's it. All right. So what do I know? I know that my x-intercept is going to be negative 1 comma 0. I know that whatever this number is, square root. Let me get the decimal because I don't even know what that is. Let me think how I even do that. All right, I got it. All right, it's negative. So I know that's going to be somewhere in between here. Hold up. Oh, Lord. Yeah, that's going to be somewhere in between negative 1 and 0. And it's going to go up to 1. So I'm just going to say it's going to be like right here, for example. All right? Just making it up. 1 second. How you doing that? There you go. That's a positive 10. All right? Asymptote, negative 2. X equals negative 2. So we already know what's going to happen here, right? Coming from negative infinity. Bam. There we go. All right, so this is y equals log, wait, is it 5 log? Hold on. Yeah, 5 log x plus 2. Okay. That's it. I should have labeled that other point too. My fault. Hold on. Made a boo-boo. So this point right here, that's the fifth root of 10 minus 2 comma 1. That's that little point right there. And that's it. Questions on this? You mean at the top? Wait. You mean up here, like this?
Oh, shit, I see how it's this way?
Yeah.
Scroll up, I think those one very good. Let's just say like, you see the vibe, that's between, that's after the log of 74.
Like where the 4 is? That's the base. Yeah, that's the base number. Yeah. You're right, right. No, when there's no number, 10 is your base. Yeah, 10 is your base. Yeah. All right. Yay. All right. I feel like we've all had enough of this. So let's just like summarize this. I don't know about y'all, but like I'm just like, eh. Because we've been through this already, you know? So let's just summarize this real quick, right? So this is the translations, right, of a logarithmic function. So now that we have worked with each type of translation for the logarithmic function, we can summarize each in this table, right? So here you go. So you have your shifts, right? Horizontally is going to be C units to the left, vertically D units up or down, right? That gives you the form log base B of x plus C plus D. If we're stretching or compressing, we're going to multiply it times the constant, right? If the constant is greater than 1, right? It's a stretch. Less than 1, it's a compression, right? You can reflect this graph over the x-axis by multiplying it by -1. You can reflect about the y-axis by multiplying the x term by -1, right? And then the general equation for it overall is y equals a log base b of x plus c plus d. All right. Y'all got calculators, y'all can verify this. All right. That could, yeah, it could be a question like that. So let's run through it real quick. So translations of logarithmic functions, all translations of the parent logarithmic function y equals log base b of x have the form f of x is equal to a times log base b of x plus c plus d, where the parent function y equals log base b of x, where b is greater than 1, is shifted vertically up d units. You're just adding that to the y. Shifted horizontally to the left C units, You're just adding that to the x, right? Shifted vertically, right, by a factor of the absolute value of a, if the absolute value of a is greater than 0. Compressed, it shouldn't have said stretch. It should have said yeah, it should have said stretched vertically, excuse me, not yeah. Compressed vertically by a factor of the absolute value of a if the absolute value of a is between 0 and 1, so a fraction. Reflected about the x-axis when a is less than 0, and then for f of x is equal to the log of negative x, the graph of the parent function is reflected about the y-axis. So it's like, instead of this, it's like that. Or instead of that, it's like that. Whatever. Verify it on your calculator before you submit it. That's all.
This key shape.
It is.
We look at it. You know what's good?
Yeah. Right.
Say, you know, say it to sweet peptide or some to the private machine.
Yeah.
Oh, you need situation.
You see it? We'll go over it, don't worry. I got you. All right, let's get to something more interesting and fun. It still involves logs, though. All right. So we're going to be using the product rules for logarithms. Hallelujah. So recall that So recall that the logarithmic and exponential functions undo each other, right? This means that logarithms have similar properties to exponents. Some important properties of logarithms are given here. First, the following properties are easy to prove. Log base b of 1 is equal to 0, and log base b of b is equal to 1, right? So for example, if I have log base 5 of 1, that's going to be equal to 0, since 5 to the 0 power is equal to 1. We saw that already, right? And log base 5 of 5 is equal to 1, since 5 raised to the 1 power is 5, right? So next we have the inverse property. Oh, this one be lit right here. Log base b of b to the x power is equal to x, right? And b raised to the log base b of x is equal to x, where x is greater than 0, right? So for example, let's say I want to do log of 100. We can rewrite the logarithm as log base 10 of 10 to the second power, right? And then apply the inverse property, which is log base b of b to the x, which is equal to x, right? So to get log base 10 of 10 to the second is equal to 2. To evaluate e to the ln of 7, excuse me, to the ln of 7, we can rewrite the logarithm as e to the log base e of 7, right? Then apply the inverse property of b to the log base b of x equal to x to get that e to the log base e of 7 is equal to 7. So finally, we have the 1-to-1 property, right? So log base b of m is equal to log base b of n if and only if m is equal to n. Light work, right? In case you're wondering, on your formula sheet, that's why I'm going fast. All right. It's about to be lit. It's the good stuff right here, the good stuff. So we can use the 1-to-1 property to solve the equation log base 3 of x equal to log base 3 of 2x plus 5, right? For x, since the bases are the same, we can apply the 1-to-1 property by setting the arguments equal and solving for x. So 3x is equal to 2x plus 5, right? Subtract 2x both sides, x is equal to 5 right there, right? Not too bad. But what about the equation log base 3 of 3x plus log base 3 of 2x plus 5 is equal to 2? The 1-to-1 property does not help us in this instance. Before we can solve an equation like this, we need a method for combining terms on the left side of the equation, right? It's the fun stuff right here. So recall that we can use the product rule of exponents to combine the product of powers by adding exponents. Just to recall, right? X to the A times X to the B is equal to X to the A plus B. Remember that, right? On the formula sheet too. We have a similar property for logarithms called the product rule for logarithms, which says that the logarithm of a product is equal to the sum of the logarithms because logs are exponents and we multiply them like bases. We can add the exponents. We will use the inverse property to derive the product rule below. So given any real number x and positive number m and n, b, where b does not equal 1, we will show that log base b of m times n is equal to log base b of m plus log base b of n. So let m equal log base b of m and let n equals log base b of n. In exponential form, these equations are b to the m is equal to m and b to the n is equal to n. It follows that log base b of m times n is equal to log base b of b to the m times b to the n, right? Which, remember, becomes what? Log base b of b to the m plus n. Put that in the front. Those are going to cancel out. It becomes log base b of m plus log base b of n. To substitute in for m and n. Dope, dope, dope. Telling y'all, this is fire right here. Yeah. All right, so note that repeated applications of the product rule for logarithms allow us to simplify the logarithm of the product of any number of factors. So for example, consider log base b of w, x, y, z. Using the product rule for logarithms, we can rewrite this logarithm of product as the sum of logarithms of its factors. So log base b of w, x, y, z is the same thing as log base b of w plus log base b of x plus log base b of y plus log base b of z. All right? Easy peasy. Good stuff, man. Good stuff. Just to recap real quick. So the product rule for logarithms can be used to simplify a logarithm of a product by rewriting it as a sum of individual logarithms. So log base b of m times n is equal to log base b of m plus log base b of n for b greater than 0. All right, let me make it real simple. Let me just show y'all how to do it real quick. I'll tell y'all that I'm gonna show y'all, all right? So given the logarithm of a product, use the product rule of logarithms to write an equivalent sum of logarithms. Here's how you do it. Step 1, factor the argument completely, expressing each whole number factor as a product of primes, right? Step 2, write the equivalent expression by summing the logarithms of each factor. All right? Good stuff, good stuff, good stuff. So here's a question. So using the product rule of logarithms, right? I want to expand log base 3 of 30x times 3x plus 4. I want to expand it, all right? So check this out, check this out, check this out. So I see that I have 3 multiplications here, right? Log base 3. I have 30 times x times 3x plus 4. Right? So very simply, what does this become? This is going to be log base 3 of 30 plus log base 3 of x plus log base 3 of 3x plus 4. Questions on that? We good? Everybody know how to do this? Y'all said that a little. Yes. Y'all said that a little too quick. What's the answer here? So log base b. Why is this thing freezing? Log base b of what? Of 8 plus, good. Plus what? Log base b of k. Very good. And that's it. All right. Yeah, that's it. You're just expanding it. That's all. Oh, we get into that. We're gonna get to that. Yeah. I mean, but I kind of showed you it already in the previous example, but we're gonna get to it. The power property, yeah. We're gonna get to that. You're gonna see it. Yeah. It's super interesting. Low key, you already know this, but I'm gonna repeat it, right? So using the quotient rule for logarithms, right? For quotients, we have a similar rule for logarithms. Recall that we use a quotient rule of exponents to combine the quotient of exponents by subtracting their powers. So x to the a divided by x to the b becomes x to the a minus b power, right? The quotient rule for logarithms says that the logarithm of a quotient is equal to a difference of logarithms. Just as with the product rule, we can use the inverse property to derive the quotient rule. So given any real number x and positive real number mn and b, where b does not equal 1, we will show that log base b of m over n is equal to log base b of m minus log base b of n, right? So to prove it, let's say that m is equal to log base b of m and n is equal to log base b of n. In exponential form, we know that this means that b to the m power is equal to m and b to the n power is equal to n. So it follows that log base b of m over n would be equal to log base b of b to the m over b to the n, which becomes log base b of b to the m minus n, right? Throw that in front, it becomes m minus n, plug back in m and n, right? And we get log base b of m minus log base b of n, right? And that's it. Good stuff, good stuff, good stuff. Let's talk about an example real quick. So for example, right? Say you have log of 2x squared plus 6x over 3x plus 9. We must first express the quotient in lowest terms, factoring and canceling. We get log of 2x squared plus 6x over 3x plus 9 is equal to log of 2x times x plus 3 over 3 times x plus 3, right? Cancel out the like terms, right? Boom. We have log of 2x over 3. Next, we apply the quotient rule by subtracting the logarithm of the denominator from the logarithm of the numerator. Then we just apply the product rule, right? So log of 2x over 3 is going to become log 2x minus log 3. But look, it's 2 times x, right? So that's going to become log of 2 plus log of x minus log of 3. Not bad, right? Exactly, just expand it. Yeah, just expand it. That's all you're doing. That's why I like this, see? Yeah. Yeah,
The final, everything is being the final.
yeah, everything's on the final. How many what?
Exercise.
I have to count. I don't remember how many's on there.
Um,
Probably 36, yeah. That sounds about right. 36, not 50, maybe like 36. Yeah, yeah. So the quotient rule for logarithms, right, can be used to simplify a logarithm or a quotient by rewriting it as a difference of individual logarithms. So log base b of m over n is equal to log base b of m minus log base b of n. All right. You do?
That's why.
Oh, the graph? I got you. Nah, don't be. After I finish this, I'm gonna ask y'all a question real quick. So let's continue. So given the logarithm of a quotient, right? Use the quotient rule of logarithms to write an equivalent difference of logarithms. Express the argument in lowest terms by factoring the numerator and denominator and canceling common terms. Write the equivalent expression by subtracting the logarithm of the denominator from the logarithm of the numerator, and then check to see that each term is fully expanded. If not, apply the product rule for logarithms to expand completely. All right, so this is how you do it. All right. So now let's look at a really, really fun question that's not on your homework. All right. Your homework questions are easier. That's why I'm saying that. But just for fun, let's knock this one out. So we want to use the quotient rule for logarithms to do this, right? Log base 2 of 15x times x minus 1 over 3x plus 4 times 2 minus x. No, we're just going to expand it. That's all right. So this is going to become what? First, you want to deal with the division. So this is going to be what? Log base 2 of 15x times x minus 1. It's all factored for us already, so we don't have to do no factoring. Minus log base 2 of 3x plus 4 times 2 minus x. That should be in parentheses right there. Boom, right? Let's go a step further, right? Because now we can use a product rule. So this is going to become log, I made that mistake. Log base 2, let's say of 15 minus, plus. Sorry about that. Log base 2 x, right? Because they'd be all being multiplied, plus log base 2 of x minus 1, right? Technically speaking, all that should be in parentheses. Minus, open parentheses, we have log base 2 of 3x plus 4 plus log base 2 of 2 minus x. Close parentheses, close parentheses. That's it. Cool, right? We're just expanding. That's all we're doing. We're just expanding. Expand the horizons. Unfortunately, the ones in your homework are a little bit easier, but at least y'all get the idea, right? For you too.
Told me to advise you, it's not looking easy. We got them triggers.
Trick not bad. Yeah. Nah, it's gonna be good. All right, look at this. Using the power rule for logarithms right here, right? So we explored the power rule and the quotient rule, but how can we take the logarithm of a power such as x squared, right? So one method is log base b of x squared is equal to log base b of x times x. We know that already, right? Which, again, we apply the product rule, which becomes log base b of x plus log base b of x, or 2 log base b of x, all right? So notice that we use the product rule for logarithms to find a solution for the example above. By doing so, we have derived the power rule for logarithms, which says that the log of a power is equal to the exponent times the log of the base, all right? So keep in mind that although the input to the logarithm may not be written as a power, we may be able to change it to a power. So for example, 100 is equal to 10 squared, or the square root of 3 is equal to 3 to the half power, or 1 over e is e to the negative 1, right? These are our powers right here. Give y'all the power rule. Huh? So here goes the power rule right here. So the power rule for logarithms can be used to simplify the logarithm of a power by rewriting it as the product of the exponent times the logarithm of the base. So log base b of m to the n power is equal to n times log base b of m, all right? That's our power rule. All right. Let me show y'all a little how-to real quick. I'm gonna run over time a little bit, just letting y'all know. The next section after this is only for those who want to use a calculator. All right. I'm about to give y'all the ultimate T. All right. So given the logarithm of a power, right? Use the power rule of logarithms to write an equivalent product of a factor, right? So here's how you do it. Step 1, express the argument as a power if needed, right? Step 2, write the equivalent expression by multiplying the exponent times the logarithm of the base. All right. Let's look at a quick example. Same thing. I just want to expand this, right? So I have log base 2 of x to the 5th power. Here's what's going to happen for log base 2 of x to the 5th power, right? The power jumps down in front. So what does this become? This becomes 5 times log base 2 of x. That's it. That's how you do the power one. All right. Questions on that? Y'all good? Yep, that's it. Yep, that's it. You know? Sometimes you could get the question given to you like this. Where we want to expand it. So if I have log base 3 of 25, I'm about to do that LG again. Log base 3 of 25, right? We know that we can rewrite 25 as what? 5 squared, right? So this would become log base 3 of 5 squared, right? The square you already know can get thrown down to the front. So this becomes 2 times log base 3 of 5. That's your answer. I'm done. Yeah, power rule. Yeah. Not bad, right? Yeah.
How many rules are there for logs? Like, is yours?
That's the last one. Well, no, that's the second to last one. Yeah.
No.
Second to last one. Second to last one. Yeah. Another thing we could do is also I could give you a log and then ask you to what you call it, expand, wait, not expand it, like in reverse. Yeah, like I could give you like a log and then same thing, expand it. Using the sum or difference here. Let me just show you another example of what I mean. This is kind of pushing everything together so you can see. Even though it's ln, you know that ln is what? Log base e. So the same rules apply here, right? So I have ln of x to the fourth power times y over 7, right? So first thing you want to do, get rid of that division. So this is going to be what? ln of x to the 4 times y minus ln times 7, right? Right, because we want to get rid of the division first, right? Now we could tackle that multiplication up top, right? So now, what's this going to become? Open parentheses. This is ln x to the fourth. Let me put that in parentheses like that, plus ln y, right? Close parentheses minus ln 7. Now, use your product rule, right? So this is now 4 ln x, right? Plus ln y minus ln 7. That's your answer. All right? That's simple. To answer your question, if it was a radical, like a square root, that's the half power, right? So that's how that would be. Hmm? But I know some of y'all might want to see it, so here it is. All right? If I have log, right, of the square root of x, right? That's the same thing as log to the 1/2 x power, right? As log x to the half power. And then you already know, right? Throw the half down, and then that's it. Right? Throw the half power down. This is going to become 1/2 times log x. You see a radical? That's what you do for the radical. All right? Ba, ba, ba. Real quick, I can ask you to condense a logarithm for me too. You'll see this on your homework where it's already expanded and I want you to go in reverse. All right. So log base 3, 5 plus log base 3, 8 minus log base 3, 2. Right. You could write this all as what? Just go step by step. Right.
But we have inverse of this, right? We didn't do that, right? Oh.
No inverse. No.
No reverse.
No inverse. Yeah. Just reverse the process, right? So this is gonna be what? Log base 3 of what? 5 times 8. Right? Yeah, 5 times 8 minus, I don't know why this thing is freezing on me. 5 times 8 minus the log base 3 of 2. Computer's freezing right now. I hate when that happens. All right. So after that, right, you're gonna go straight into the division. So, why is this thing freezing? Log base 3, 2. That's a minus, right? There we go. Okay, we're back on business, right? So now, final answer, log base 3 of 5 times 8 divided by 2. Simple, right? You can do the math. I know y'all know how to do 5 times 8 divided by 2. Y'all know how to do the math on that. But that's how you would condense it. If it comes expanded, this is how you condense it. Addition becomes multiplication. Subtraction becomes division. All right? That's simple. Go ahead.
They don't have the same thing. How?
You can't condense it. No, it has to have the same base. Yeah.
So, now the base 10 equal as 11, right?
Or ln wouldn't have a base, yeah. If it was log base 10, it would just be log. If it was ln, it would just say it means log base e, but it'll just be ln. Yeah. Hmm? Right. Also, the multiplication times the log, that becomes an exponent. That's another part. All right.
So the example in logarithm is exponential.
It'd be a mix, maybe. A mix. Yeah.
Then for the model, it can be for the model we did the example.
We're still learning some stuff. I got you. Yeah. So real quick, for those that want to use the calculator, 2 seconds, 2 seconds, 2 seconds. All right, look. This is gonna be I got you. This is the change of base formula for logarithms right here. This formula right here is magic. All right. So most calculators can evaluate only common or natural logarithms. So on your calculator, it can only do base 10 and base e. But I'm not asking you no base 10, base e question. I got base 2, base 5, base 9, you know? So how do we do that in the calculator? This is how, right? So we use the change of base formula to rewrite the logarithm as a quotient of the logarithm of any other base, right? So when using the calculator. So to derive the formula, here it is. Log base b of m is equal to log base b of n to the m divided by log base n to the b, right? So let me just show y'all an example, and y'all then we'll get up out of here. Here you go. All right. So real quick, if I give you this question, right? What is log base 5 of 36? And you wanted to do it in your calculator, right? You could use whatever you want. You could use the ln, you could use log base 10, it don't matter, right? You do have it on the calculator. Yeah. Where it says log, right? Press second and log. That's how you use it. All right. You press second and then log. But here's what I want you to see, right? The question, yeah. Here's what I want you to see. The question is log of base 536, right? The big number is your numerator. The base number is your denominator. So if you're doing this in ln, for example, this would be ln 36 divided by ln. Hold on, I don't know how to write ln. ln of 5. That's it. You click enter, you get this number right here. All right? That's all it is. If you don't want to use ln, you want to use log, that's fine. Log of 36 divided by log of 5. Enter, boom, there's the answer. This is how you answer a question that doesn't have a common base to it, meaning it's not 10 and it's not E. All right? This is how you do it. All right? Or if you have a fancy calculator like you could just put the regular base in and it does it for you. You know? Yeah.
So was the unnecessarily either.
Yeah.
It's just.
Yeah. That's how you do it in like for you need that.
Yeah.
Yeah. Yeah. You can, but not everybody else can. Yeah. Like you could type in the first part, log base 5 of 36 to enter and get the answer. Um, I'm just asking for the answer. Give me the answer. All right. You should show your work because if it's wrong, then that's how you get extra points, right? Change a base formula. This is my jam right here. Right? Can be used to evaluate a logarithm with any base right here, right? So for any positive real number m, yeah, same thing. It doesn't matter which one, right? Right? So for any positive real number m, b, and n, where n does not equal 1 and b does not equal 1, the log of base b of m is equal to ln m over ln n of b. All right? So use any one, it don't matter. Whichever one you want to use, it'll work. And that's it. That's a change of base formula. Really, really powerful. Can help you answer any question that you might have. And then that's it. Like these are for the number problems. Yeah. Just click enter. No, just click enter and then it goes for you. You don't have to convert it. You just do it straight in the calculator. Yeah. Real quick, step by step, this is how you do it in the calculator. This is just for those gonna watch the recording, right? So given a logarithm with the form log base b of m, you use a change of base formula to rewrite it as a quotient of logs with any positive number n where n does not equal 1. So step 1, you want to determine a new base n, remembering that the common log of x has base 10 and the natural log ln of x has base e. You want to rewrite the log as a quotient using the change of base formula. The numerator of the quotient will be the logarithm with base n, and the argument m. The denominator of the quotient will be a logarithm with base n and the argument b. That's it. All right. So let's call it at that. Stick around. I want to ask y'all a question.